topic I'm talking about is the changing role of humans in structural design, but actually this applies broadly to design in the AEC industry. In recent years, the rise of data-driven computing and forms of artificial intelligence, such as machine learning, have started to gain traction in the preliminary design stages, offering insights into project feasibility and helping to develop and test concepts against specific criteria under human supervision and direction. It's apparent that the power and application of digital tools is accelerating and rapidly changing the role machines play in our design conversations, evolving from those that are closed to those that are more open, and therefore traditionally more human-centric. In doing so, we're dissolving historical boundaries and opening the door for machines to directly influence the what. There's a table on the screen here, and we can see how these roles are being challenged in structural engineering. In this particular case, it's for the design of horizontal elements in a building, reflected in more open goals, more complex inputs, less transparent algorithms, and more data-rich inputs. This is just an example. However, there's now a plethora of emergent technologies that can be used as part of a how to design system to engage in increasingly open conversations, sometimes as proprietary software or modules, for example, Autodesk Refinery, or more commonly using bespoke workflow solutions, developed actually with relatively low cost or open source tools, such as Grasshopper, with plugins such as Millipede, Galapagos, or Peregrine. Here we can see solutions developed by some of these tools as a critical part of these open design conversations. Rapid advances in technology are going to allow our conversations to continue to become more open. An example of this is the release of the Generative Pre-trained Transformer, or GPT-3, which was released by OpenAI last year. And it's already been applied to a broad range of applications, including, for example, the writing of software code. So this shift from closed to more open conversations is also apparent from the way, from the elevation of machines in the overall design process. However, something more non-trivial, the process of design isn't represented by a singular flat conversation, but rather levels of conversations all interacting with each other, the goal of each one providing feedback to the one above. Here we can see this for the design of a typical building structure. Firstly, there's an overarching high-level conversation, for example, design a building structure. This will be broken down into general subsets of the what, each forming a mid-level conversation, for example, design a stability system, which can then be broken down further into low-level conversations that explore very specific subsets of the what. For example, design a coupling beam. These how to design systems, they may be distinct at each level, they may be connected or fully integrated depending on the level of automation and interoperability of any of the software employed. At each level, there's a distinct observer who's watching that process, but the observer will receive feedback from the conversations via the respective feedback loops that ultimately inform the overall what. Now, as technology enables our design conversations with machines to become more open and delivers increasingly connected multi-level how to design systems, we're effectively inviting machines to influence the what, not just for these low-level conversations, but also for higher levels of conversation. From a cybernetic perspective, we're also replacing human observers with machine observers, typically from the bottom up. And therefore, we're introducing the potential for greater process and decision-making opacity. As we do so, we risk inadvertently abdicating our responsibilities with less and less oversight of our design processes and diminishing control over an understanding of the outcomes. The objective of creating these more open design conversations with machines is to arrive at an optimum partnership where the skills of humans and the computational capabilities of machines can execute better quality designs, deliver greater design efficiency, achieve faster and more consistent production, produce more design options, but also minimize our own solution bias. As highlighted, these opportunities come with consequences such as less transparent algorithms, more complex inputs and goal definitions, and a significant increase in output data. These risks all need to be identified and managed if we're to generate maximum value from our design conversations with machines. It's therefore likely The key components to successful human-machine partnerships are going to include the following factors. Firstly, smoother, more efficient conversations delivered through improved data management and interoperability, reducing manual effort and minimizing the risk of errors. Secondly, better human-machine interfaces for improving visualization and assessment of computer-generated options, and to facilitate an understanding of increasingly large and multidimensional data sets. Also, a focus on developing human-centric skills such as problem setting, critical thinking, creativity, and an understanding of the concept of holistic value, so we can set appropriate goals and identify those best value solutions. On a practical level, we should be building specialist in-house knowledge and skills to look under the hood of these technologies, such as coding, data science, and artificial intelligence, to effectively leverage their capabilities and mitigate some of the risks. And then finally, we need to be developing processes to understand these conversations, such as documenting and reviewing our workflows, identifying the how parts of the conversation and the what parts of the conversation, and driving informed decisions regarding what are human roles and what are machine roles.